For those of you that were concerned, don't be. We're going to have a quick Lavoisier review and then go into elements. So it will be a review to the degree that you were able to pay attention to the video yesterday. I just thought it was better for you to see past me do it and then current me do it than to give you a day of just reading and making your flashcards for elements and things like that. So if you didn't feel comfortable with yesterday's presentation, don't worry, we're going to cover the important aspects today in class. So quickly to go back to Antoine Lavoisier. If you Google this guy, you'll see pictures of him and his wife and sitting there with some rudimentary chemical equipment and things like that on the picture. But he's known for this law of mass conservation. Remember, the idea here is that matter cannot be created and that matter cannot be destroyed, but it can only change forms. Now, I'm not going to say that Lavoisier believed this, but let's think for a second about creating things. What do we tend to believe in terms of where did things come from? And we're a Christian school, so there's your hint. Where did things come from? God. God initiated. God was the one, remember we talked about, who created ex nihilo. He's the only one that's been able to make something out of nothing. We as creatures have been given the privilege of making things out of things, but we don't make things out of nothings. We are able to take the basic building blocks, again, my Duplos, right? Basically, God makes all the blocks, and then we get to drop them. No, we get to reorganize them in different ways so that they look different, but we haven't made anything new other than the arrangement of what was old. That's an important principle in chemistry and theologically, that we don't create something out of nothing. God does that. We get to rearrange his some things into other things. But if we break it down to the basic building blocks, we didn't make the building blocks. We arranged the building blocks. This idea of mass conservation says this idea that, hey, I've got something, I've got some kind of a structure, and if I go ahead and I rip it apart, well, I had one structure, but now I have 3 different structures. And the structures don't look like what I started with, but I haven't created anything other than made things which are different than the original, but I've made them out of the same pieces. So if I start with blocks, and our analogy would be I'd perform a reaction upon that big structure, and in the end it looks differently. Let's say I take these 3 pieces and I react them such that they come together, they look different, I've got something different, but I haven't added or taken any blocks away. I've just made them look different. And so in that sense, matter cannot be created or destroyed, it can only change forms. That's what chemistry does. It takes the building blocks that God has given us and rearranges them, but in the end, we have no more, no less blocks. We've just made them look like something else. Okay. So that's the law of mass conservation. Since I don't make anything and I can't destroy anything, the fundamental pieces that I have don't change. And since the fundamental pieces, the stuff I started with, is technically the same stuff I end with, I have no more or less stuff. I have no more or less mass. I have the same mass. Okay? I've beaten that horse to death, I think. Does anybody still have a question on the law of mass conservation? The principle behind it. Again, it's not weight. Weight is the force of gravity upon a mass. It's mass. It's matter. How much stuff I have. So Lavoisier's law of mass conservation. Well, application of this, you see the reactants and products, and the mass of the reactants equals the mass of the products. That was from 2 days ago. So we have that principle at play in here. Since I haven't made anything, I haven't destroyed anything, I've got the same stuff, then the mass before and after have to be the same. Going to this idea of elements then. Through decomposition, and I mentioned before that decomposition in chemistry is not the same as decomposition in biology. In biology, I think I told you that biology decomposition is ooey gooey, smelly, slimy, right? Biology decomposition is something dies in the corner and you don't find it for a week and a half. When you go over to find it, you find it in some sort of decay. That's a biological decomposition. In chemistry, when we use the word decomposition, it's a lot less stinky, smelly, and gross. Decomposition in chemistry is basically I have something that's large and I break it up into something smaller. I take this and I break it up into something to smaller pieces. But let me get technical. Ultimately, what I'm doing is I'm breaking everything down until I get fundamental components. These fundamental components. It's a little bit tricky up here with this limited workspace and using one hand. But if I take that big structure I had before and I break it down and I bring all the pieces that are similar together, now, question is, have I added any duplos? Have I lost any duplos? I'll tell you there's none on the table, okay? So I've got the same I started with. Have I created or destroyed any mass? Do you see that they look fundamentally different? You also see that I've broken it down into, in this analogy, I've broken it down to blues, reds, greens, and yellows. Do you see that if I try to keep all the colors the same, I can't take apart these structures into anything other than blue, red, green, or yellow? Or to get more specific, let's say that I break it down to, in this whole big decomposition, all these pieces are in play, but I break it down into one of my pieces is a single blue duplo. Okay. I had a big structure that I could break down into other structures, I could break down into other structures, I could break down to other structures. Now we get to the one duplo. What can I break it down into? Nothing. I can't break it down anymore. Okay. When they get to the place where they can't break it down anymore, this building block that I can't break down anymore, it's referred to as an element. In this imagery here, I've got a large section. Let's say I break it down into 2 sections. I break it down into 3 sections. If I can't break it down anymore into any smaller pieces, I then would say, when I can't break it down anymore, I have what is known as an element. Now, let's stop for a moment and think of Aristotle and Democritus. Aristotle said in his continuous theory of matter that you could break matter down into smaller and smaller pieces, right? Indefinitely. Now, we had a larger structure that we broke down. I broke it down into a single, one of the pieces was a single blue, but here were single yellows and single greens. Just the fact that my structure is not all one color says we kind of agree with Democritus more, right? If I have a compound that has one element, another element, and other pieces, they have different kinds of building blocks all stuck together. When I break it down, I have different piles of different things. That would lead me to think Democritus was right. Democritus said, in a discontinuous theory of matter, that when you have something, every building block of that thing is not the same building block. Matter of fact, there's no such, for Aristotle, for continuous theory, there's no such thing as building blocks. There's just stuff. And you get smaller and smaller and smaller and smaller pieces of the same stuff. Democritus says you break it down and you find that there are different things that are hooked together that look like a whole, look like one thing, but in actuality, like the grains of sand at the beach, when I get closer, think of them as different colors of sand. These are different colors of sand that when they're all together, look like sand. From a distance, a bunch of these would look like a solid chunk of sand, but it's not. It's made up of granules of different kinds of sand that come together. Okay. So, when we get to this point, though, we even further start to agree with Democritus, because if I had a single piece here, Aristotle would say, I can cut that into a smaller piece and a smaller piece and a smaller piece. But see, we get to the place here where suddenly we're down to the building block, the element, and I ask this question, can we, kind of jumping around a little bit here for structure, but later on we'll know that one piece of an element is known as an atom. Okay? So one atom of this element. Can I break that one atom into smaller pieces? So I've got a yes and a no. Which is right? No? Okay. The answer is yes, I can break it down into smaller pieces, but when I break it into smaller pieces, I no longer have an element. I have subatomic particles. So I have an element. Let's say I have an atom of blue. Here's our chemical or element blue. If I break it in half, do I have two blues? No, I no longer have a blue. I have common pieces. We find this out later. People theorize, and we discover this in chemistry. I no longer have an atom of blue. What I have are pieces of atoms which are common to everything. See, we later find out that those pieces that make up this one atom are common to virtually every element. The same subatomic pieces make it up. Neutrons, protons, electrons, and so on. Those subatomic particles make up this one atom. But this one atom has a unique mixture of those things, which is unlike any other atom. So it's kind of a combination of we can't break it down anymore, but we can. But when we break it down more, it's no longer what we had. But the law of mass conservation is we haven't created or destroyed anything when we break it down even farther than the one atom. So for right now, for what we're talking about in terms of elements, let's think of it with regard to a compound, which is the next section. A compound is when you have multiple elements that come together to form a structure. Right here I have a structure which is made up of purely red. And we could argue that I have 3 atoms of red. These 3 atoms of red come together, and now I have a chunk of red that's made up of individual pieces of red. But if I break it up anymore, I no longer have red. I have parts of an atom. I no longer have a full atom, a full structure. And even this concept of atom comes from this Greek philosophy. So we're not going to push into the philosophy too much, the basic subatomic particles. But when you get to the piece that can't be divided anymore and still be identified as one consistent basic building block, then we get to the place of the element. Elements as opposed to compounds. Now, any substance that cannot be broken down or decomposed into any simpler components. And what I mean by that, and maybe clarify that, as I just said, we can't break it down anymore and still have what we call an atom. We can break it into pieces. Later on we get the Dalton and people like that will explain in a little more detail. But for right now, we can break it down into pieces, but not still have a full piece known as an atom. If we can break it down into 2 different atoms, then it's a compound. We can only break it down into 1. If they're all blue, then we have an element. Okay. So chemists went through a time of discovery. If you think of it as decomposition, they're decomposing all these substances. They have all these structures, and they're chemically breaking it down into the lab, and they're discovering that there are basic building blocks, common building blocks, that make up the larger structures, the larger molecules, the things that we're more familiar with. We tend not to have pure elements hanging around. We tend to have things that are made up of mixtures of things. And so chemists went through and empirically devised what we know as the periodic table. I heard you all had some fun yesterday with, is it in the front cover of the book? Is it on page 52? We all have 3rd edition. The deal is there are 2 printings of the 3rd edition, and there are reasons for that. If you look at your book and you have the periodic table behind the front cover, I believe that means you have the first printing of the 3rd edition. If you don't have the periodic table on the front cover, you have it on page 52. Matter of fact, if you have the first printing, you have it on 52 as well. So that's not an issue of whether you have it or not. I'll caution those of you that have the first printing. Why do you think they gave a second printing? Yeah, there's mess ups in first edition. And frankly, I have both books, and I taught from first printing, not first edition, first printing last time, and now I have a second printing book. But we will get to places where there are going to be minor errors on your own answers and things like that, which I'll try to highlight for you. There's not the majority of them, but they're there. And there are a few places you'll go, but Mr. Baker, I don't understand. Even I look at the on your own and it doesn't match what we've been talking about and teaching class. How can that be? If you have the first printing, that may be something we haven't caught. So I'll try to find a list and get an errata sheet to you, which means, hey, first printing people, these are the changes you need to be aware of because they were corrected in the second printing. And again, I know some of the reasons for why they printed it again and why they didn't just do another edition, but that's not important for the class. So we'll leave that off this discussion and the video and go back to the periodic table. So the periodic table is a graphical way of showing all the potential building blocks that we have. Everything that we know is made up of things that are on that table. Think of it this way, that every element over there, and I've got a periodic table there on the wall, I'll put one up here on the board, that the periodic table is a graphical listing of all the duplos that God has made. So every block on there represents a different kind of duplo that God has put into your play box. And everything that you can make, and there are some rules that exist, and that's what chemistry is about, the rules that exist on how you can build structure out of the duplos that God has given us. Okay? There are certain rules that we have to follow. There are certain ways the duplos go together. But as long as we play with the duplos in that way, and frankly, God doesn't allow us not to, He controls the operations of those duplos and how we use those duplos. But we make things out of the blocks that He's made, but we don't make blocks. We can't make blocks. It's beyond our ability to do. Now, in the lab, you push back on that a little bit, and you say, but in the lab, Mr. Baker, they can have synthetic elements. We can create things in the lab. We can add an extra proton to something. We can, in the lab, build a duplo. The thing of it is, when we build them, they fall apart sometimes within microseconds. We have elements that exist in the lab that don't exist in nature because we force a subatomic piece into an existing duplo to change it and go, boom, we created something. We better take a picture of it quick because God's going to destroy it in a microsecond because it's not part of the plan of the duplos He's given us to work with. See? So we push against that idea of we can't make something out of nothing by making something different out of something that was made. And there are laws of God, the character and nature of God in play that prevent us from doing some things that we might like to do. Again, there's a technical, chemical, quantum mechanical answer for all these things, but that's good enough for the scope of this course. What kind of information is on this periodic table? Well, there are 118 boxes. Is that still true? We've got some new ones that were discovered. This one on our wall over here goes up to 109. Okay. What about in the book here? What do you have? It goes up to 118. Yep. So there are some over there that we've added to the periodic table through discovery. Matter of fact, in the history of the periodic table, it's kind of interesting. The periodic table was designed and devised, and the placement of future to be discovered elements were in there. At different periods in history, this periodic table, and I don't want to cut too much over the camera, it's right here, it's right there for you here in the classroom. The periodic table was actually devised and had blanks, and scientists went out to try to find the pieces that go into the blanks. I mean, it was so, the structure of it became so clear on how it was built that they basically built they built the development and they waited for the houses to show up. Said, oh, this block, we just found what goes there. It's this, as they placed it. So we have a video later on in the class. It's one of those, when I'm sick at the last minute, throw this video on that goes through the development of the periodic table. It's kind of cool. So if that doesn't happen during the course of during this course, we'll watch that at some point intentionally. The search for the elements. So each block on the periodic table represents one element. It represents one building block, one potential building block that we can use. Those building blocks can't be broken down into another building block. When we break down the building block, it's still matter, but it's no longer an atom or a single piece of a known element. So everything that has matter, everything that we can see, and the matter around us that we can't see, is made up of those blocks. Let me advance this a few to get on that so I can just leave it in place and talk through a few notes here. You'll notice on the blocks they all have abbreviations. Do you remember from the video yesterday where those abbreviations come from? Some of them make perfect sense and others don't. For example, for me, hopefully it makes sense to you that carbon is a C, a nitrogen is an N, an oxygen is an O. But I think on the video I talked about Na is sodium. We get sodium from natrium. Natrium is the Latin name for sodium. So if you know Latin, Na is obvious to you. If you don't know that sodium is also known as natrium in Latin, then you're here going with sodium. That must be an S. No, sulfur is an S. Sodium is Na. So every element is identified by one or two letters. Those one or two letters come from either the English or the Latin name. Reason for that is, as I said, this chart was in development by multiple scientists at the same time in different places. And so when they came to standardize them, they went with either the English or the Latin names. Some were already identified and they already had Latin names, so they kept them. Others didn't have Latin names, they had English names, so they kept them when they brought it together. Which is why, I think I referred to page 77, there's a chart in there, and those elements that are in bold on that chart are ones that you simply have to memorize. You should expect quizzes and on future exams that when one of those bold elements is used, that you'll be expected to identify it. You're not going to be told, you know, do a reaction that includes calcium, nitrogen, and oxygen, and they're not going to say the symbol for calcium is Ca, for nitrogen is N, and for oxygen is O. You're going to be expected to know that. So that's one of the things you need now to just start memorizing. I think I encourage Miss Jessica to tell you, make flashcards now. Just drill yourself on them. What is the name of this element given the symbol, and then then work it the other way. Here's the symbol. What's its name? You should be able to go from sodium is Na to Na is sodium. Just becomes second nature to you to identify, especially those bold ones on that chart. One of the most significant things we're going to also look at is the jagged line. I'm going to go over here to the on-wall periodic table. If you notice here, this is column 13 is the new designation. I still go with, I'm an old guy, right? This is column 3A to me. But you'll notice that right here, we've got boron, then the line between aluminum and silicon. Then over here, just see the jagged line? It's in red on this chart. On the chart here on the slide, it's this heavy bold line right here, the stair-step jagged line. It's critical for you to know where that line is at and what it means. Every element, and it's here on the slide, every element that is to the right of that jagged line, so it's to the right of this stair step, everything on that side we're going to consider to be a non-metal. And everything to the left of that jagged line, including those things which are under the jagged line, which is the majority of things, we're going to consider those to be metals. Now, there are certain characteristics of metals and nonmetals. There's some physical characteristics, and there's some properties that you need to have memorized. First of all, metals. And again, those are the things that are on this side of that jagged line. Metals are characteristically malleable. 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 Okay? What does malleable mean? Yes? You can what?
You can mold it.
You can mold it. You can shape it, right. If I take something that's a metal, and this is going to be generalities. There are some exceptions, but again, they're pushed beyond the scope of the course. But for right now, it's either metal or non-metal. There are metalloids, which surround this jagged line. And the metalloids have properties of both. They're not really fully either. They're kind of transitional things. But right now, let's talk about the basic cases. For a metal to be malleable means, and if you need an image for this, if I take a chunk of it and I put it on an anvil and I smack it with a hammer, a metal is going to be reshaped. It's going to be flattened. I can take a metal and by impacting it, mold it and shape it and create something else. So in contrast to that, what do you think a non-metal is going to be? What's the antithesis of malleable? What's brittle? That's the word that's used. So it's malleable if it's a metal, it's brittle if it's a non-metal. So if I take something that is a non-metal and I put it on an anvil and I smack it with a hammer, mentally, what am I going to imagine is going to happen? Yeah, it's going to blow up into chunks. It's going to break. It's going to fall apart. So a metal, if I hit it, I shape it, I mold it, I create something out of it. That's why you don't typically have non-metal jewelry, right? Because you take the metal, you want to shape it. You have goldsmiths that shape it. You put patterns on and prints on it. Non-metals don't hold that. You try to shape them, you break them. So general characteristics. If I have something and I can shape it, it's probably a metal. If I have something that if I put a lump of coal, which is mostly carbon, and like a piece of charcoal from your barbecue, smack it with a hammer, I don't expect it to flatten out. It's going to break into pieces. It's a non-metal. Don't think in your mind metals are solids and non-metals are not solids, because sometimes people think that. They look up here and they see the oxygen and nitrogen and the chlorine and all the gases, and they're going, oh, it's not a metal because it's a gas. No. What it appears to us to be in terms of is it a solid, is it a liquid, or is it a gas, is typically where in the domain of conditions where we live. Remember we said before about we tend to be able to thrive. Let's be honest, we live basically between freezing and boiling, right? If we get higher than boiling, we cook. If we get lower than freezing, we freeze. So we're kind of creatures that have to be in a certain range. These elements don't share our biological need. They will continue to exist in their form at all different temperatures. Every single element on the periodic table can be, under the right conditions, pressure and temperature, can be a solid, a liquid, and a gas. It can be all three. We just may never live to see it naturally in that phase. So for example, if I say calcium. Calcium, we tend to see it as a solid. It's in pills we take, we calcium for our teeth and all this kind of stuff. So in the temperature and pressure range where we live, we know calcium as being a solid. If on a test I said, is calcium a solid, liquid, or gas? The answer would be yes. I need more information, Mr. Baker. Is calcium a solid, a liquid, a gas at standard temperature and standard pressure? It's a solid. Now I've told you at what temperature and pressure, I'm asking you to tell me, is it a solid, liquid, or gas? It's called its phase. More detail later. So what does it look like, solid, liquid, or gas? That's all dependent upon the temperature and pressure. A few other things we can talk about, but basically if you keep in mind, hey, I know iron as being solid, but you know what? We have forges that heat it up and turn it into a liquid. So if I ask you, is iron a solid or a liquid, you would say at room temperature or in the blast furnace where it's melted. Because in the blast furnace, it's a liquid. Here in everyday life, it's a solid. See the difference? So, question. Is iron a gas? Could be, right? Is it now at this room temperature? No. But at a certain temperature, do you realize that everything would vaporize? And when it vaporizes, it doesn't mean it's turned into something else. It's just iron in gaseous form. And when it was cooler, it was iron in liquid form. And when it's even cooler, it's iron in solid form. So whether it's a metal or a non-metal has nothing to do with whether it's a gas or a liquid or a solid. That's a completely different question. Okay? And I just know people get hung up on that sometimes, so keep that in mind. First we did malleability. Metals, shapeable. Non-metals, brittle, they explode. Second characteristic, metals have luster. Luster. I take this Academy ring, I think maybe 2 or 3 times I've cleaned it, right? Some of you have precious jewelry you clean on a regular basis. You take it out and you shine it up, right? Because metals, by nature, take a shine. They have luster. You put a light on them, they sparkle, they glow, they reflect, they project. That all happens with a metal. Non-metals lack luster. So some of you academically are metals and some of you are non-metals. Some of you lack luster. Sometimes we hyphenate that and say you're lackluster, okay? But metals shine, non-metals don't. Again, going back to that analogy of the barbecue briquette, I might decide that I want to have a shiny lump of coal. and then go out and shine it up. And yes, I know there's hard coal and soft coal and all these different kinds of coal, but basically, as a general statement, coal doesn't shine up well. Okay? So we don't have things that we think are precious because of their glow and their shine that are nonmetals. We have metals that do that. We go shine the tea service. We go, or maybe you don't anymore, but you go shine those things up. So maybe jewelry is a good analogy. You know, if you hit your ring too hard, it's going to bend. Metals are malleable. You know, your ring, if you clean it and buff it, it's going to shine because metals have luster. Nonmetals don't. They have lackluster. Metals malleable, nonmetals brittle. Metals luster, nonmetals non-luster. And then lastly, has to do with a chemical or a property of electrical conductivity. Metals conduct electricity. Nonmetals don't. Again, metalloids, and under certain situations we can force some current through certain things, but for just the broad definitions, metals conduct electricity, nonmetals don't. Wiring, for example, in homes. What is most wiring made out of? Yes, sir. Copper, right? We have copper wiring. We have metals in the wiring because electricity will travel through. Electrons will be bumped out is a better way to understand it, but electricity travels through those wires and goes throughout the home. It would do us no good to have wires that are made out of nonmetals. We'd plug them in and nothing would happen because they don't conduct electricity. Metals conduct, nonmetals don't. And so you can see where you might be asked a question, hypothetically, that you're given a substance and you notice that a current passes through it. Is it a metal or a nonmetal? You're going to assume it's a metal because metals conduct. If it was a nonmetal, it would not conduct. If I said you have a wire that conducts electricity, if you take the coating off of it and you try to buff it, will it take a shine? Yes. Why? Because it conducts electricity, which means it's a metal, and metals have luster, which means I can buff it and get a shine out of it. If I take that same wire and hit it with a hammer, will it flatten or break? It will probably flatten. Why? Because it's a metal and metals are malleable. So you can know something is a metal or non-metal and then expect certain characteristics to come out of it, or given an object and say, does it shine, does it bend, does it conduct? To figure out whether it's a metal or non-metal. Any questions on that? Those characteristics of metals and non-metals? Okay. All right. That being the case, there are some exceptions to the jagged rule. There's always exceptions, okay? This jagged rule, this jagged stair-step rule between metals and nonmetals. The exceptions are, I've already mentioned them. There's the metalloids. The metalloids have properties of both metals and nonmetals. So you might have a metalloid that conducts but doesn't have a luster, that's brittle but conducts, you know, things like that. But for the scope of this course, we're going to stay away from those. You're going to be protected from those. You're just going to have to tell me metal or nonmetal, and we're going to assume the metalloid, based upon where it sits on the jagged step, is either acting like a metal or a nonmetal. And the one that becomes the most obvious over time but is the most difficult at first is hydrogen. Hydrogen on the periodic table sits right over here. Now, is it left or right of the jagged line? It's presented over here on the far left end, okay? But hydrogen is actually a nonmetal, and it should be, for the purposes of metal or nonmetal determination, it should be shown on this side right next to helium. It should be. But there's more information on here than just simply is it a metal or nonmetal, and for reasons we'll get to later, it does belong over here graphically because there's a more important thing at play that we're not to yet, okay? So if on exam you're asked, is hydrogen a metal or a nonmetal, you need to remember it's left of the jagged line, which would make me think it's a metal. However, it's the exception. It should be over on the nonmetal side. On your own, 2-2. Goes through and lists a series of elements and just asks you, are these elements metals or nonmetals? Basically says, are they metals, yes or no? Okay? We're going to take a moment and try to find the element, determine whether it's a metal or a nonmetal, and then we'll see if we're right. Okay, so the first one they ask for here is sulfur. Sulfur, so you should have your periodic table in front of you. I'll give you the elements. You just try to find them. It's kind of a, you'll come to learn where they're at, but initially it's just a matter of scanning and trying to find the symbol. Sulfur is a symbol S. Take a moment, try to find sulfur on the periodic table. And when you find it, note above it what column is it in. This will become important, much more important later on. But like for example, I'll do the first one over here on the board. Sulfur is over here. Atomic number 16. Remember from yesterday, that means it has 16 protons, and when it is a neutral atom, has 16 electrons. It is in column 6, 6A, okay? So sulfur right here, 6A. Is that symbol to the right or to the left of the jagged line? To the right. By virtue of being to the right of the jagged line and not being an exception, sulfur is a metal or a nonmetal. Okay, so this arrow up here shows you sulfur is over here in column 6A. It's to the right of the jagged line. It exists in the domain of the nonmetal. So if I were to ask you, does sulfur conduct electricity? It's a nonmetal. It does not. Does sulfur take on a luster when you buff it? No, it's a nonmetal. If I smack a chunk of sulfur, would it shape or break? I would expect it to break because it's a nonmetal. Okay? Calcium. Calcium has the symbol Ca. And one thing I failed to mention at that time, every element has its own symbol, 1 or 2 letters. The first letter is always capital. The second letter is always lowercase. So if you had capital N, capital A, it would be wrong. Capital N, lowercase a is sodium. Okay? It has to be an uppercase and then a lowercase letter. So sodium, natrium is Na. You locate natrium on column 1. Or excuse me, is it calcium or sodium? It's calcium. Forgive me. Calcium is in column 2. It's Ca. Atomic number 20. The column 2, Ca. Right now we're just asking, is it to the left or to the right of the jagged line? Obviously, it's to the left. It lives in the domain of the metals. Calcium is a metal. Astatine. Atomic symbol At. If you were to go pecking and hunting and trying to find astatine, it's not near the top, it's more near the bottom of the main table, the lower right-hand corner, and you would eventually find it at the bottom of column 7, 7A. Knowing that astatine lives in the bottom of 7A, and its position there is right on the stair step, but it's to the right of the line, correct? So astatine is a metal or a nonmetal? It's a nonmetal. Mm-hmm. Thallium. Thallium is your next element you're asked to find. It also is in that last full row on your periodic table. Actually, second to last row. Atomic number 81. They're all in order, so find 81. Thallium. In your book, it's in the standard section there. It's in green. If you looked at the key, it said it's in the standard metals area. So what is it? It's a metal, and for our purposes, it's to the left of the jagged line. It's right here, thallium. It is underneath the stairs, but it's to the left of the line. And because it's to the left of the line, we're going to consider that to be a metal. Hassium. Hassium exists on that last line as well. It's in this middle section called the transition metals, and we'll talk about that in more detail later on. But it's right here, and because of where it's located on the periodic table, obviously on this one that I have on the slide, it's in the transition metals section. But for our purposes, in your book, you just have this jagged stair-step line. It's to the left of the line, therefore it is a metal. Xenon. Xenon is an interesting, in our temperature pressure range, gas. It's over on the right hand column, far right, column 8, 8A. Find out later that these are called the noble gases. There's a reason why they behave the way they do. But now just looking at this address, this placement of the element on the periodic table, is it to the right or left of the jagged line? Right of the jagged line meaning that it is a metal or a non-metal? Non-metal. And the fact that these are often called the noble gases, that's why I don't want you to get confused thinking that it's a non-metal because it's a gas. It's a non-metal because of its properties and its temperatures and pressures that we tend to exist in, that they're gas at that temperature and pressure. But they're not non-metals because they're gases. Last one, hydrogen. Hydrogen is the most basic element, has the fewest subatomic particles in it. It's presented here on this table, right up here, top left corner. Is it a metal or a non-metal? It is a non-metal because it's the exception. It is the element that's on the left. It's left of the jagged step, but it's the exception because it should be, for this purposes of metal non-metal, it should be depicted over here in the non-metal section.